Okay, we are going to continue today with vectors. Now suppose you have two vectors, A and B. This is your vector A. Let's remember what the vector was. It tells you the address of the point, how to get there, if it's a position vector. Geometrically, a vector is equal to just its three coordinates, remember. And our vector A is AX units along the x-axis, then some number AY walk along the y-axis, and the number AZ walk along the z-axis. Okay, we remember that. So we can make a picture of the vector, or we can write it as its three coordinates. Now suppose you want a displacement by the vector A, so you get to the point AX, AY, AZ, and then there's another displacement, this time by the vector B. So the meaning of A plus B geometrically is clear. Okay, it's just get to A and then follow another displacement by BX in the I direction, BY in the J direction, and BZ in the K direction, starting from A. So A plus B is just the vector A followed by the vector B. And now I can write the expression for A plus B. What is the x component of this? How far is this displacement in the x direction? Well, it's AX plus BX in the x direction. Remember, I is the unit vector, just one unit of going in the x direction. Okay? Plus AY plus BY in the y direction, plus AZ plus BZ in the z direction. Geometrically, this is the vector A plus B. Is this clear? Because starting from the origin, this is where you end up finally, and the geometric representation of A plus B is then just the diagonal of the parallelogram, the figure you make with these two vectors. Now, as you can see, it doesn't matter in what order you write these numbers, which are the coordinates. AX plus BX is the same thing as BX plus AX. Geometrically, this means if you get to this point the other way, so the first vector you took off from the origin is B, and then you turned around and did the displacement A, of course you get to the same point. Algebraically, since the definition of the vector sum is just adding up its components. Okay, it doesn't matter in which order you add these components. Ax plus bx is the same thing as bx plus ax, so a plus b is the same thing as b plus a. And if you make a picture, you just draw your two vectors, complete a parallelogram, and draw the diagonal starting from the origin, put the arrow ending at the final point. That's your vector a plus b. Is this clear? Bu mikrofon çalışmıyor herhalde, değil mi? Ben sesimi yüksek tutmaya devam edeceğim. Arkada herkes duyuyor herhalde. Önde de duyuyor. Tamam. Okey. Sen alıyor musun? Bu çalışıyor. Tamam. Okey. Now, what about a vector minus b? How do you think the vector minus b is defined? Any guesses? What are the coordinates of minus b? Geometrically it's the opposite direction, but in terms of numbers coordinates, if b is 3, 2, minus 1, 3i plus 2j minus k, okay? If that is b, what is minus b? Minus 3, minus 2, plus 1, right? You just reverse all the numbers because obviously, I mean, vector is just its coordinates, minus that vector is all the coordinates minus. And geometrically, as your friend said, it means going in the opposite direction. So let me write that down. Minus b is simply minus b sub x I minus b sub y j minus b sub z k. And now let me draw that. Here is minus b. And if I now want to do subtraction, I just take the vector minus b and add it to a. So here we go. A, here is a minus b, or minus b plus a, it's the same thing. And here's our vector a minus b. So this is very straightforward. Addition of a vector or subtraction of a vector is just doing those operations on the coordinates. Okay, and the geometrical meaning is obvious, clear, right? Any questions about this? Okay. Now what about multiplying vectors? Multiplication of vectors. Well, for multiplying two vectors, it turns out there are two different kinds of multiplication. So we'll do both of those. This way of multiplying two vectors is defined as the multiplication of their components. Which components? Well, ax, bx. That's a multiplication. Then multiply the y components, ay, by, and multiply the z components. So now you have three products. Product of x components, product of y components, product of z components, you add them. That is the definition of how to multiply a vector. Okay? This is a mathematical definition. Remember, whenever I make a definition, something that doesn't come from experiment, but just some new terminology, I use the three-line equivalence sign. Okay? What am I defining here? I'm defining a mathematical operation, this dot. Okay? I'm defining a kind of multiplication. By convention, this multiplication of two vectors is indicated by a dot. And I'm defining what this dot means. Okay? So it's an operation that I'm defining. It's an operation on two objects. Both things are vectors. Okay? What is the result of this? Is this a vector? ax, bx plus ay, by plus az, bz. Ax is ax a vector by itself? Ax is 3. Is 3 a vector?
Just that. Just the point.
Ax, ay, az is a point. Just the number ax, is it a vector or a point? Only ax. It is not even a magnitude, it's just a number. I mean, we only learned vectors in this course in the last lecture. Before that, we had numbers. Ax is such a number. A vector is 3 numbers. Each